This presentation is brought to you by Jimmy Backflow Productions. This presentation focuses on interpreting the double check valve device assembly (DCVA) test results, and is one of a multi-part production. Analyze the test results for the double check valve backflow prevention device assembly. The purpose of testing a backflow prevention device assembly is to determine if it is working correctly, meets the standards established by the industry, and provides protection. Furthermore, the test results provide essential information for evaluating the operational condition of the backflow prevention device assembly. Therefore, the certified tester must analyze the test results methodically before giving the backflow prevention device assembly a pass or fail condition. Part 1. Backpressure Evaluation Test. The double check valve device assembly (DCVA) is an inline testable and repairable backflow preventer, conforming to the American Society of Sanitary Engineering 1015 standard for controlling direct cross connections. Backsiphonage and backpressure. A DCVA is designed to prevent the backflow of water and constructed to operate under intermittent or continuous pressure conditions. The DCVA temperature range is 33.0 degrees to 140.0 degrees Fahrenheit, 0.6 degrees to 60.0 degrees centigrade. Double check valve device assembly design conditions. The double check valve device assembly includes the following: 2 independently acting spring-loaded check valves, coupled within one body, which are internally force-loaded to a normally closed position. Check valves equipped with a 1 pound per square inch minimum spring. Properly positioned tightly closing resilient seated upstream and downstream shut-off valves. 4 appropriately located test cocks. Note: the American Water Works Association's maximum allowable pressure loss for a double check valve device assembly is 10 pounds per square inch for all sizes. Double check valve device assembly ASSE 1015 performance requirements. The test procedures discussed in this presentation systematically evaluate the ability of the DCVA to meet minimum performance requirements established by the following: the American Society of Sanitary Engineering, the University of Southern California Foundation for Cross-Connection Control and Hydraulic Research, and the American Water Works Association. Test the DCVA when installed, annually, and immediately after repair or when returned to service. Testing ground rules for DCVA. Note A. The DCVA check valve shall close drip tight effectively to control backflow. The effectiveness of the DCVA in controlling backflow is determined by measuring the differential pressure across the check valves when the DCVA is in a no-flow static state. The pressure loss across the DCVA check valves shall not be less than 1 psid. In addition, the second check valve shall be drip tight against backpressure. Note B. The upstream shutoff valve does not have to be closed when measuring the differential pressure across the check valves using 3-valve test kit, high and low pressure hoses. Note C. The protective aspect test of the DCVA can be conducted using the high and low pressure hose method if the downstream shutoff valve is not closed, or closed but not drip tight, provided that the DCVA is in a no-flow static state and absent of backpressure at test cock 4. Note D. The backflow test kit records a differential pressure reading across the check valve if the DCVA is in a static or dynamic state. Therefore, a no-flow validation test shall be performed to confirm the position of the check valves. Note E. The pressure at test cock 4 shall be less than the inlet pressure to measure the differential pressure across the second check valve using the test kit, high and low pressure hoses. Testing a DCVA using a 3-valve differential test kit. Testing protocol. The DCVA test is performed to confirm the pressure loss across the first check valve is a minimum of 1 psid. The pressure loss across the second check valve is a minimum of 1 psid, and drip tight against backpressure. And a no-flow static state existed at the time of the test. When measuring the differential pressure across the check valves, using the test kit, high and low pressure hoses, it is essential to perform the test when the double check valve device assembly is in a no-flow static state. In addition, back pressure must not be present at test cock 4. The test seeks to determine if the check valves close drip tight. Suppose the differential pressure across the check valves is measured when water flows through the DCVA due to a not closed or closed but not drip tight downstream shutoff valve with downstream demand. In this case, the test kit gauge records a differential pressure, but the recorded differential pressure was conducted on open check valves. The test kit gauge records a differential pressure because as water flows through the DCVA, the water pressure is reduced, thus generating a differential pressure. Consequently, testing the double check valve device assembly in a dynamic or flow state adversely affects the test outcomes and does not assess the protection aspects of the DCVA. Pre-testing conditions. Consider back pressure. Before measuring the differential pressure across the check valves of a DCVA, the DCVA is tested to comply with the standards and to determine if protection is provided. Before performing the test of a DCVA, it is essential to evaluate the presence of back pressure at test cock 4. If back pressure is absent at test cock 4, proceed with assessing the protection aspects of the DCVA. However, if back pressure is present at test cock 4, the downstream shutoff valve is not closed, or closed but not drip tight. In this case, the second check valve evaluation, against the standard, cannot be conducted using the test kit high and low pressure hoses, since if performed, the test kit gauge would register a 0 psid across the second check valve. Understanding the ramifications of testing with back pressure is critical to attaining valid test results to assess the protection aspects of the DCVA. Pre-testing requirements. 1. Examine the installation of the DCVA for proper installation before testing. 2. Identify and evaluate the type of water downstream of the backflow prevention device assembly. 3. The downstream shutoff valve should be closed after permission is granted. 4. The test cocks should be flushed. However, take caution when flushing test cock 4, because, if the downstream shutoff valve is not closed drip tight, and back pressure is present, the water coming out of the test cock may be compromised, and could cause harm to the tester and surrounding area. To prevent uncontrolled water discharge from the test cocks, connect a transparent tube to the test cocks when flushing, and use a bucket or proper receptacle to catch the discharge. Determine if a back pressure situation is occurring by conducting the Backpressure Evaluation Test. Backpressure Evaluation. Step 1. Note: downstream shutoff valve closed and test cocks flushed. Step 1. Connect a standard pressure gauge with a bleed valve arrangement to test cock 1. Open test cock 1. Next, open the pressure gauge bleed valve arrangement to bleed out any air. Once the air is removed, close the gauge bleed valve arrangement and note the gauge reading at test cock 1. Backpressure evaluation. Step 2. Note: upstream shutoff valve open, downstream shutoff valve closed, and test cocks flushed. Step 2. Close test cock 1 and remove the pressure gauge. Next, connect the same standard pressure gauge arrangement to test cock 4, open the test cock, bleed out the air, and note the gauge reading at test cock 4. Assessing the results of the Backpressure Evaluation Test. No back pressure. If the pressure at test cock 1 is higher than at test cock 4, back pressure is not present at test cock 4. Proceed with the test of the backflow prevention device assembly. Note: the results indicate that back pressure was absent at test cock 4. The results do not validate the status of the downstream shutoff valve. For example, the downstream shutoff valve could be closed but not drip tight with no back pressure. On the other hand, the downstream shutoff valve could be closed drip tight, with back pressure present. Assessing the results of the Backpressure Evaluation Test. Equal pressure. If the pressure at test cock 1 is the same as at test cock 4, back pressure may or may not be present at test cock 4. Furthermore, the equal pressure may indicate that both checks are not drip tight. Additionally, the downstream shutoff valve may or may not be closed drip tight. In this case, proceed with the test of the backflow prevention device assembly. Note, if both test cocks have the same pressure, the double check valve device assembly is in a no-flow static state. There would be a drop in pressure at test cock 4, if demand were downstream, due to the fundamental laws governing fluid flow in a pipe. Fluid flows from high pressure to low pressure. Assessing the results of the backpressure evaluation test. Backpressure. If the pressure at test cock 1 is lower than at test cock 4, backpressure is present, and the downstream shutoff valve is not closed, or closed, but not drip tight. Address the backpressure issue before conducting the test of the DCVA, using the test kit high and low pressure hoses. Testing the differential pressure across the check valves, with backpressure using the high and low pressure hoses, generates erroneous results. For instance, measuring the differential pressure across the second check valve would result in a reading of 0 psid, even if the second check valve is drip tight. If the second check valve is not drip tight, the first check valve reading results in a 0 psid. Caution. If the downstream shutoff valve and both check valves are not drip tight, and if backpressure is present at test cock 4, and the pressure recorded at test cock 1 is remarkably higher than the expected line or inlet pressure, non-potable water may be flowing into the potable water system. Assess the situation immediately. Justification for evaluating backpressure. Backpressure at test cock 4 affects the test results. Suppose backpressure is present at test cock 4, but not substantiated. In this case, the test kit gauge registers a 0 psid when measuring the differential pressure across the second check valve, using the high and low pressure hoses connected to test cocks 3 and 4. A 0 psid reading indicates a not drip tight second check valve. However, this assessment may not be accurate. For example, the second check valve may be drip tight, and the cause for the 0 psid reading is the high pressure water downstream of the second check valve. The existence of backpressure at test cock 4 may also impact the first check valve differential results if the second check valve is not drip tight. In addition, the backpressure assessment test confirms that the downstream shutoff valve is not closed, or closed, but not drip tight, if backpressure is present at test cock 4. This slide shows what happens when the differential pressure across the check valves is measured using the high and low pressure test kit hoses, with backpressure present at test cock 4. The graphic in the upper right shows what occurs when measuring the first check valve differential pressure, when backpressure is present, and the downstream shutoff valve and the second check valve are not drip tight. The bottom left graphic shows what occurs when measuring the second check valve differential pressure, when backpressure is present, and the downstream shutoff valve is not drip tight, but the second check valve is drip tight. In this illustration, the differential pressure across the first check valve is measured using the test kit high and low pressure hoses connected to test cock 2 and 3. In this case, the first check valve registers a 0 psid. The 0 psid indicates that the first check valve is not drip tight due to a damaged disc, seat, or debris. In rare cases, the 0 psid reading results from a damaged or missing check valve spring. However, the conclusions could be misleading if backpressure was not assessed. For example, as shown in the diagram, if backpressure is present and the second check valve is not drip tight, high pressure water passes through the second check valve and culminates downstream of the first check valve. In this case, perform the backpressure assessment test to confirm the cause of the 0 psid reading across the first check valve. If the assessment indicates that backpressure is present at test cock 4, the downstream shutoff valve is not closed, or closed but not drip tight. However, the status of the first check valve is unknown, until the status of the second check valve is substantiated. Because of the back pressure, the differential pressure test does not confirm the status of the second check valve, but generates dubious results. Therefore, to confirm the status of the second check valve against back pressure, take the water pressure reading at test cock 1 and 3. If the water pressure at test cock 3 is higher than the test cock 1 water pressure, the second check valve is not drip tight against the back pressure. In this case, the cause for the 0 psid reading is back pressure downstream of the first check valve. In this illustration, the differential pressure across the second check valve is measured using the test kit high and low pressure hoses connected to test cock 3 and 4. In this case, the test kit registers a 0 psid across the second check valve. The first check valve registered a 1.0 psid. The second check valve 0 psid indicates that it is not drip tight due to debris, a damaged disc, or seat. In rare cases, the cause of a 0 psid reading could be a damaged or missing check valve spring. However, the conclusions could be misleading if back pressure was not assessed. For example, as shown in the diagram, if back pressure is present, and the downstream shutoff valve is not closed, or closed, but not drip tight, high pressure water is downstream of the second check valve. In this case, perform the back pressure assessment test to confirm the cause of the 0 psid reading. If the assessment indicates that back pressure is present, at test cock 4, the downstream shutoff valve is not closed, or closed, but not drip tight, and the cause for the 0 psid is the back pressure downstream of the second check valve. In addition, since the first check valve recorded a differential pressure, the second check valve is drip tight against back pressure. If the second check valve were not drip tight against back pressure, the test kit would register a 0 psid across the first check valve. Back pressure consideration. Suppose back pressure is present at test cock 4. Consequently, the downstream shutoff valve is not closed, or closed but not drip tight. The next step is to consider the extent of the back pressure. To do so, close the upstream shutoff valve and open test cock 2. Possibility A. If the water stops flowing from test cock 2, the upstream shutoff valve is drip tight. In addition, either the first or second check valve, or both, are drip tight against back pressure. The next step is to open test cock 3. If the water stops flowing from test cock 3, the second check valve is drip tight against back pressure. Proceed with measuring the differential pressure across the first check valve using the high and low pressure hoses, but first, close the test cocks and open the upstream shutoff valve. Additionally, because of the back pressure, use an alternative method to measure the pressure loss across the second check valve, or curtail the back pressure before testing the second check valve. Alternatively, repair or replace the downstream shutoff valve before conducting the DCVA test. If the water continues to flow from test cock 3, but not 2, the first check valve is drip tight, but the second check valve is not drip tight against back pressure. In this case, the protective aspects of the DCVA cannot be assessed by measuring the check valve's differential pressure, since the test kit would register 0 psid. In this case, repair or replace the downstream shutoff valve before conducting the DCVA test. Possibility B. If water continues to flow from the test cock, the upstream shutoff valve is not drip tight, or both check valves are not drip tight against the back pressure. In this case, repair or replace the downstream shutoff valve before conducting the DCVA test. Upstream shutoff valve tightness test with back pressure present. Situation 1. Suppose the upstream shutoff valve is closed and back pressure is present at test cock 4, but water continues to flow from test cock 2 and 3 when open. Since back pressure is present at test cock 4, the downstream shutoff valve is not closed, or closed but not drip tight. Hence, the source of the water flowing from the test cocks is inlet water passing past the upstream shutoff valve, or high pressure downstream water, passing through both check valves. To determine the source of water discharging from the test cocks, measure the pressure at test cock 1 and 2 using a standard pressure gauge. If the pressure at test cock 1 is lower than at test cock 2, the upstream shutoff valve is drip tight, but both check valves are not holding drip tight against backpressure. Therefore, the water discharging from the test cocks is high pressure downstream outlet water. Upstream shutoff valve tightness test with backpressure present. Situation 2. When determine the source of water discharging from the test cocks, suppose the water pressure at test cock 1 is the same as at test cock 2. In this case, open test cock 2 and 3. S1. If the water stops flowing from test cock 2 and 3, the upstream shutoff valve is drip tight. In addition, the second check valve is drip tight against the back pressure. S2. If the water stops flowing from test cock 2, but continues to flow from test cock 3, the upstream shutoff valve and first check valve are drip tight. However, the second check valve is not drip tight against the back pressure. S3. If the water continues flowing from test cock 2 and 3, this indicates that 1. The upstream shutoff valve is drip tight, but the check valves are not drip tight against back pressure, or 2. The upstream shutoff valve is not drip tight, but the check valves are drip tight against back pressure, or 3. The upstream shutoff valve and check valves are not drip tight, or 4. The upstream shutoff valve and the second check valve are not drip tight, but the first check valve is drip tight. Note, if S3 number 1 occurs, non-potable water flows into the potable water system. Backpressure is present. What's next? Testing a DCVA with backpressure present, downstream of the second check valve. Suppose backpressure is downstream of the second check valve, at test cock 4, and suppose the backpressure cannot be addressed by closing the downstream shutoff valve drip tight, or eliminating the backpressure. In this case, measuring the differential pressure across the second check valve, using the high and low pressure hoses, is impractical, since the results would be a zero differential pressure reading on the test kit gauge. However, it is possible to measure the differential pressure across the first check valve, using the high and low pressure hoses. Accordingly, there is an alternative test procedure that can measure the differential pressure across the second check valve, with backpressure at test cock 4. This test procedure is described in the Manual of Cross-Connection Control, 10th edition, published by the Foundation for Cross-Connection Control and Hydraulic Research, University of Southern California. Backflow concerns. The certified tester's knowledge of the water usage downstream of the DCVA installed for cross-connection control is imperative, since the water downstream is non-potable. Consequently, consider the water quality concerns and risks associated with the non-potable water before flushing test cocks, especially when opening test cock 4, if backpressure is present. It is possible that exposure to the compromised water from test cock 4 causes harm to someone or something if backpressure is present. Note: the water downstream of a DCVA installed for service line protection is considered potable, according to plumbing code requirements. However, if the internal plumbing system is not compliant with the plumbing code relating to cross-connection control, the water quality downstream of the DCVA installed on the service line is compromised. Therefore, take appropriate measures to correct the non-compliant plumbing system, since water consumers are at risk. Test cock 4. Closed. Backpressure. In this illustration, the storage tank fills to an elevation equal to system pressure. 1.0 pounds per square inch equals 2.31 feet of water. However, if the inlet water pressure drops below the tank water head pressure, and the tank valve is open, the high pressure water, backpressure, pushes against the second check valve. Consequently, if the second check valve is drip tight, the DCVA protects the potable water system from the tank water. In this case, there are no health or safety issues if test cock 4 remains closed. Test cock 4. Open. Backpressure. In this illustration, backpressure is present at test cock 4. However, if the first or second check valve is drip tight, the DCVA protects the potable water system from the tank water. Subsequently, opening test cock 4 for an extended period, with the downstream shut-off valve open, or closed but not drip tight, impacts the hydraulics downstream of the DCVA. Additionally, due to the water quality downstream of the DCVA, flushing test cock 4, with an open downstream shut-off valve, is a health and safety concern. Alternative procedure for assessing backpressure, using the test kit. Not recommended. Backpressure can be assessed by connecting the test kit, high-pressure hose, to test cock 4, and the low-pressure hose, to test cock 3. If backpressure is present, the test kit needle records a differential pressure reading. Conversely, the test kit needle records a zero differential pressure reading if backpressure is absent, since the high-pressure hose is connected to the low-pressure side of the check valve. This procedure is not recommended, since the water downstream of the DCVA is non-potable, which is introduced into the test kit. The exception is the installation of the DCVA on the service line, for service line protection. In this case, the water downstream is potable. The procedure previously mentioned in this presentation is the preferred approach for assessing backpressure. This illustration demonstrates the procedure to assess backpressure using the test kit. Not recommended for DCVA installed for cross-connection control. The concept is to connect the high-pressure hose to the anticipated check valve high side, in this case, test cock 4, and the low-pressure hose to the anticipated low side of the check valve, in this case, test cock 3. Then, proceed with the steps for measuring differential pressure. Caution: the water entering the test kit through the high-pressure hose connected to test cock 4 is non-potable and contains substances that could cause damage to the test kit. The exception is DCVA installed for service line protection. In addition, if backpressure is present at test cock 4, and the downstream shut-off valve is open, or not closed drip tight, and if the first check valve is not drip tight, and the high and low control valves on the test kit are open, as well as test cock 3 and 4, a cross-connection is created. This configuration allows non-potable water into the potable water system. Again, the exception is DCVA installed for service line protection.